Well, I won't say it's a pleasure to welcome Dirk König because this is his home and I've wandered across from chemical engineering. But it's a great pleasure to introduce Dirk. He has long background in physics and solid state physics and electronics engineering. As a quick summary of his career to this point, he studied at Chemnitz in Germany, obtained his diploma in 1997, spent 3 years as a research engineer at Chemnitz before pursuing his PhD studies between 2000 and 2003 at Chemnitz. He then was involved in postdoctoral research with AMD Europe, also in Dresden, and also associated with Chemnitz University for a couple of years to 2005, at which point he made the transition down under to beautiful Sydney, and has been since 2005 working with the photovoltaics activities here at UNSW in the ARC Centre of Excellence and subsequent evolutions thereof. Since 2015, Dirk has also been wearing a second hat as Deputy Director of Research with the IMDC. So Dirk is going to be talking about some analytical work he has been doing on bonding arrangements and morphologies in zinc-blende nanocrystals today. Pass over to you then, Dirk.
Thank you very much, Sean, for the introduction. The title says zinc-blende nanocrystals, but because we have the same space group symmetry, TD space group for diamond lattice materials, only the base is different. It's not AB like gallium arsenic, but silicon-silicon. These results derived here also apply, obviously, to silicon. As you shall see, I mostly talk about silicon simply because I do most calculations with silicon. But these results also apply to zinc-blende materials like zinc-blende itself and 3/5. Quick look at the outline. I will give a quick overview of the zinc-blende nanocrystal types we look at in terms of analytics, and come then to the key variables we use. After that, I go to a graphical description of the nanocrystals, because that's more intuitive and I think better to understand, at least if you got good visualization. And then I come to a couple of hands-on examples. The first one is the most simple crystal. So there I kind of take you by the hand and show step by step how we derive these formulas. And then we have a glimpse on a more complex crystal type, which has two different surface facets. And then I'll come to the applications showing different parameters and how they relate to stress phenomena and size phenomena of nanocrystals. Eventually, I'd like to wrap up. I'm not going to torture you with the maths. If you're interested in that, you see the DOI at the bottom. That's all in there. I mean, it's not the complete derivation of the equations, because that's a lot of pages. I didn't publish yet. Okay, so on the crystallites we look at, we have the 7 different types here. So we have cubes with exclusive 111 faceting. We have octahedra with exclusive, 001 faceting, octahedra with exclusive 111 faceting. We have dodecahedra with 110 faceting. These are by far the most complex to be described. We have pyramids with 111 oriented side facets and 001 base. We have tetrahedral pyramids, which are obviously all limited by 111 facets. We have two types of quadrodecahedra. One is 001 dominant. That means you just have 8 of these 111 triangular shaped facets. And if you cut these further in, you actually get a dodecahedron which has hexagons with 111 orientation and smaller squares. This, you can actually visualize that as a face-centered Brillouin zone reciprocal space, whereby the dodecahedron is from a body-centered cubic lattice in reciprocal space. Why do I stick to these rather low indices of the facets? That's simply given by the surface energy, because they have the lowest surface energy up to 433 orientational facets, in particular the 111 facet. And as we shall see with experimental data, this has consequences for at what size crystals start to grow and how they basically how they shaped. You know what facets they are limited by. You see that these crystallites have all a very different shape. So in order to compare their size, we have a simplification. We presume that they're all spherical, so we calculate a nanocrystal diameter. What you could do is you could actually use the number of nanocrystal atoms, but this is not very, very graspable because it's just a volume size, and it doesn't give you any clear idea how big the crystal really is. So that's a kind of a simplification to make these crystals comparable amongst each other. Now we see here a bit of a graphical insight of the crystals. I color-coded the outermost atoms here for the interface bonds. That will actually go throughout the presentation. So the red ones are usually located at 111 surfaces, or in that case 110, and have one external bond. The blue atoms are either on O1 facets like here or on edges or corners. And they are all one-oriented and have thereby two interface bonds. And occasionally, you have atoms with three interface bonds, like here with a pyramid at the sides. And what we derive there is 3 analytical number series per crystal type. The first one is the number of nanocrystals forming the entire crystal. The number of atoms forming the entire nanocrystal. Second one is the number of bonds forming the entire nanocrystal. And the third one is the number of interface bonds, so basically connecting the nanocrystal to its exterior. And with these 3 parameters or analytical series, we can come up with very useful results. The first one is the ratio of bonds per nanocrystal atom, so internal crystal bonds. And that gives us a good insight on external stress of the crystal. Then we have the number of interface bonds relative to the number of internal bonds. Again, that's important for the stress balance. So for instance, nanocrystal shape, or quite important, a lower limit of crystallization of silicon nanocrystals. And the last one is the number of interface bonds per nanocrystal atom. This is mostly important for the electronic structure. So if you have interface dipoles, interface charge transfer, especially in dielectrics or terminations with high electronegativity, so like fluorine, chlorine, oxygen, nitrogen, that is quite decisive. And obviously, that's all a very mathematical, geometrical construct. So you can use these descriptions for any nanocrystal spectroscopy technique. So I'll talk a bit about Raman, but you can use it for PL. I touch a bit on EPR. Yeah, anything which describes crystallography up to TEM, APT, etc. So I said that we look at the graphical interpretation of these crystals, which give you actually a better handle on things. And the cubic form of zinc-blende nanocrystals with exclusive O1 faceting is it's pretty straightforward. You got an 8-atom unit cell, and you just keep extending that into each spatial direction with 1 unit cell. So you end up with a silicon 8 cube, then silicon 64. That's 3 powered by 3 is 27, 216 atoms, then 64, 8, 512, 125, 8, 1024. That's 1768, I think, yeah. So basically, you got this, the description of the nanocrystal atoms is fairly straightforward. As we shall see, the description of the interface bonds and the bonds amongst the atoms is more complex. Then we come to the octahedra. You can also see there's clearly a system behind it. You always got these 6 corner points. You got 1 facets. We'll have a closer look at these. The dodecahedra are fairly complex, but if you actually go to the biggest crystal, you can actually see the rhomboids here. And here, for instance. And these are also complex because, strictly speaking, this is not 1 number series, but it's 2 number series. So you have an odd series and an even series. And you can see actually the even series has 1, 2, 3, 4 atoms which are exactly at the corner point between the 3 rhomboids. And so they have 3 interface bonds, whereby these, or the odd series, don't have that. So that again is from the even series. You got two two green atoms here with 3 interface bonds, another 2. So that's a bit more complex. We come then to the tetrahedra, and you can actually drive that further with the description of the atoms. For instance, the number of internal atoms, if you look here, you got 1. You put the next plane in, it's 3. Put the next plane in, it's 6, 10, 15, 21, 28. And this actually, the plane you put in, has always is actually the sum of natural numbers. So 1, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, etc. So I can see actually you can drive that further for the description or mathematical description of these crystals. These pyramids are mostly interesting for pyramidal quantum dots in 3-5s. So if you have stress balance growth, which is another application actually for these number series. And the 2 quadrodecahedra you see down here do also occur in silicon, and they are actually quite relevant in electron paramagnetic resonance, as we shall see. Okay, in hands-on example, we'll start with the octahedra with exclusive 1-1-1 faceting. The smallest one of that kind is a silicon 10 cage. You see the 6 corner points, and you have 8 facets, 1-1-1 facets, but only 4 of them have a single atom. So that one, and the rear one, the front one, there isn't even an atom. So what you have is actually you got 4 bonds plus 0 bonds, and you got 6 times the 2 bonds, gives you 16 interface bonds. And when you go to the next bigger crystal, you can see we kind of put in planes which have basically a bigger extension. And the numbers I put in referring to the next smaller nanocrystal are shown in green here. And you can see that there's a kind of a system. That's actually difference here is 2, difference is 4, difference is 4. Here it's 1, 2, 2, 3. And if you look at the number of interface bonds, you see that's 4 squared, that's 6 squared. And that goes on. You see here that's 8 squared, 10 squared, and so on. And same actually here with the distance between the number of bonds and atoms. So again, that's 1, 2, 2, 3, 3, 4, 4, 5. And here again, 2, 4, 4, 6, 6, 8, 8. And that keeps going. So here now you see that's 12 squared, 14 squared, etc. That goes then respectively higher numbers. That goes all the way to the biggest crystal I visualized, which is also the biggest crystal we can calculate in DFT. A couple of words actually on DFT. It's quite interesting because these symmetry arguments allow us to calculate such big crystals at all. There's a lot of publications out there where people take a central atom and draw a sphere in say in a diamond or zinc-blende lattice and cut out any atoms which are beyond that sphere, so they have an approximant. And that's very logical, it makes all sense, but it's in terms of symmetry, it's a very bad idea because you can't actually fold your state space into the smallest element where you can calculate all these crystals. And it's one of the secrets why we can push it actually to 3.3 nanometers. Now on the derivation of the number series, we start with the number of nanocrystals. And I just put down the number of atoms here, nanocrystal atoms. And what we do first is we calculate the differential quotient. So basically the difference between each step. And we see that follows a clear scheme. So that's 3 squared, 5 squared, 7 squared, 9 squared, 11 squared, etc. And we have to relate that in some way to the running index. So we have actually an offset. And then we just multiply the running index with 2, and that sum is squared. But what we also have is an offset because the zero element of the number series is a single silicon atom. Obviously, it doesn't have any bonds to any other silicon or 3,5 atoms. So it's just a single atom crystal, so to speak. What we do then is we use this differential quotient, and we can basically say the ith member of the number series minus the I-1 member of the number series gives us the differential quotient. That's its definition. And we just have, I mean, it's a very simple rearrangement. You end up with a recursive formula. Then we can unravel this recursive formula, and you will see if you use n-1, the n-1 member, you get basically 2 times I-1 plus 1 squared, and you go on, n-2 members, and so on and so forth. And you end up all the way to 2 times 1 plus 1 squared, which is the 9. What you do then is you just convert this recursive series into a sum. And it's really that easy, because you take the differential quotient and you sum that up from the first member, or basically the I equals 1 member, up to I. We still have to carry along the offset. And then you just basically multiply out the running index of the sum and basically split it up in the respective powers, put in the sum formulas. So that's, for instance, simply I, because you add up 1 I times with the offset, and eventually you get the result. So that's fairly easy. The bonds, there we do not have an offset there, because obviously if you got a single atom like here, methane, there is no inter or internal bond within the crystal, because it's a single atom. And this derivation is a bit more intricate, because you see you have the differential quotient, but that doesn't appear to make any sense. You got 12, 40, 84, 144, 220. Yeah, it's not really, it's no square or anything related. So if you, I mean, it's difficult to describe, you need to see that. If you look at it and you divide it by the running index, you actually see you get a very nice dependence, you know. So 12 plus 8 is 20, 20 plus 8 is 28, 36, 44, etc. And if you relate that to the running index, you see you have an offset of 4. So that gives you actually 8 times the running index plus 4. And because we already divided the differential quotient, we have to multiply to getting back to the differential quotient, and that gives us the difference, which we again put into a recursive series. And then here it's actually even easier. You just take 1 to 1 the differential quotient, and again split up these different sums, and you end up with the description of the bonds of the nanocrystal. The number of interface bonds, the description actually is very easy. I mean, you've already seen this, like 2 squared, 4 squared, 8 squared, etc. Basically what it is, you can multiply out the 4 here. So we get 1, 4, 9, 16, etc. So that's always 1. I mean, the square within the brackets always 1 counter ahead of your running index. And you can simply put that into a direct explicit form. So you don't even have to use any recursive scheme. This is just to remind you that we compare the crystals with a spherical description. Okay, a more complex example. Probably should explain the graph on the right-hand side first. This is a quadrodecahedron, which is 1-1-1 dominant. That means you got the hexagon here, like these 6 blue atoms. The hexagon is actually shown here. And you got the squares, all 1-oriented squares. I mean, the surface orientation is all 1. And this legend tries to picture that in a 2-dimensional way, so it's kind of better understandable. We see this is the number of atoms per row. So you see you got 1 blue atom, 2 blue atoms, 1 blue atom. And the black numbers are actually the number of bonds. So I got 1 bond, 1 bond, 2 bonds, 2 bonds, 1 bond, and again 1 bond. And that carries on. And the color of the atoms gives you the number of interface bonds, right? So we got 2, 4, 6, 8. And so per 4 by 2 basically per 0.1 square. And this way we can actually describe the quadrodecahedral crystals quite well. So that carries on. That's the second member of the series. Again, actually, if you go back, interface bonds appear to be very easy. Again, that's 8 squared, 14 squared. So the difference is 6. So it's probably something with 6 times the running index. But obviously, there's an offset because 8 squared is not 6 times 1 squared. And so that's carrying on, as you can see. So that's 400 is 20 squared, the bonds. And that's probably hardly readable. This is a silicon 4672 crystal. Could be also gallium 2336, arsenic 2336, because it's, as I said, it's only the base which makes the difference in the crystals. Size is around a bit bigger than 5.5 nanometers, and eventually the formulas we get for the nanocrystal atoms looks a bit more complex as for the octahedra. For the bonds, same thing. And for the interface bonds, we see the formulas again quite simple, and we can even go further and divide the total description into a partition of the all 1 facets, so all the squares, and a partition of all the 111 facets, so all the hexagons. And this will turn out to be very important for either crystal size or crystal morphology identification in EPR, so in electron paramagnetic resonance. I'll come to the applications. First one is actually the number of interface bonds per nanocrystal bond, and that has a significant influence on stress balance. And so from a certain, or below a certain size, the embedding matrix actually controls the nanocrystal shape as well as nanocrystal size. And we see that here quite nicely. That's a work from 2008 from Godefroy and Zacharias. They have a 3 nanometer crystal which has octahedral shape. You can see the 111 planes, and that is the member of I, or basically I equals 6 member of the number series, so silicon 969. And the resemblance is obvious. So they also came up with the fact that the dominant crystal form up to 3 nanometers is this octahedral form with 111 faceting. And that's simply for energy reasons, because the lowest surface energy you have is 111 faceting. Unless you go very far out in indices like 433, but then if you want to hit another bond with a 433 index, you need a crystal which is much bigger. Otherwise you can't define a plane. Now, there's also a work dating back to 1994 from Yorktown Heights. They etched back porous silicon after oxidation, and the smallest crystal size they came up with was around 1.5 nanometer. Now, if you now look at the ratio of interface bonds to nanocrystal internal bonds, we get a value of 0.41. So 0.41 interface bonds per nanocrystal bond, below which crystals form. And it also becomes clear then why these 111 faceted octahedra are dominant up to 3 nanometers, because they have the lowest ratio. So they grow first, so to speak. And beyond 3 nanometers, it gets increasingly polymorphous, so you get other structures as well, multiple facetings, etc. The interesting bit is that you can connect that to Young's modulus, so basically the material hardness. And for instance, these data are for silicon nanocrystals and silicon dioxide. If you have silicon nitride as an embedding matrix, or you start with silicon-rich nitride, the minimum crystal size should be bigger. And also the dominance of these 111 faceted octahedra should carry on to larger crystal sizes. So you can use that very nicely actually to predict, or basically to pick an adequate material system for a crystal size as you need it. Now I come to the ratio of interface bonds to nanocrystal atoms, or per nanocrystal atom. And this obviously depends on the density of interface bonds. So it's dependent on faceting, but also on the ratio of surface atoms to all atoms which form the zinc-blende nanocrystal. So as an example, if you got a cubic or 1 faceted nanocrystal and you stretch it to cubical, then you have a constant density per square area on your facet, but because you change the surface to volume ratio, basically gets bigger, you have actually bigger influence in terms of charge transfer and interface dipoles. And that's interesting because you can look at crystals where it was shown actually in the literature, not only by us, but by other people as well, that you have a dominance of the embedding dielectric up to 7 nanometers of crystal size. And these crystals are usually not cubic. They are rather spherical or octahedral. What you can do then is you can extrapolate the value you have of interface bonds per nanocrystal atom to a cubic nanocrystal with or exclusive O1 faceting. And that goes actually to 12 nanometer, well, diameter. That means actually its edge length is around 10.5 nanometers. However, if you have a FinFET, this is a cubicle, it's stretched. So you could easily stretch it to 30 nanometers and make it like 3-4 nanometers thick. You still would have the same ratio. That means the dielectric dominates the electronic behavior. This is quite interesting actually for the 40 nanometer technology. And below, obviously below. Because what you could do, as I will show on the next couple of slides, is you could produce electronic devices without doping. With the interface charge transfer, I just put in a couple of slides here because most people will not be familiar with it. It's fairly new research. So back in 2008, we started calculating silicon nanocrystals with number of surface terminations. I will just focus here on hydroxyl groups emulating silicon dioxide and amino groups emulating silicon oxide. And what we observed is that we have a 1.5 electron volt upshift of the highest occupied states and a 2.1 electron volt upshift of the lowest unoccupied states, independent of size. You can see that over size, there's not really tremendous dependence. There is a dependence when you got hydrogen termination, which is very covalent to silicon, but not if you got a strong anion. We also saw an increase of the band gap, or basically of the energy gap of the nanocrystals, and that was observed in experiment. There was a paper in 2004 by a Korean research group in Applied Physics Letters, and in 2013 there was a review by the Slalui group from Strasbourg, and they actually gathered quite a number of literature data to show that. And this interface charge transfer is a surface effect, so it should scale as the square of the diameter of the nanocrystal. And we can see that here very nicely. And we can also see, because it not just depends on the nanocrystal diameter, but also on the number of bonds on the respective facets, that this has an influence as well, as I said earlier. So this is exclusive 1-1-1 faceting. We look along O1 direction, so that's an octahedron. This is the same octahedron, but you see we have the corners cut off. So we have O1 orientation here. That means you got more interface terminations. And you see both have the same number of fluorine atoms at the interface, but that crystal with the cut-off corners has less silicon atoms. And although it has less silicon atoms, it's higher ionized. So that actually makes the point that it's not just, basically it's both. It's surface orientation as well as surface area versus volume. Now this was all theory, and yeah, I'm not very happy to trust the theory if I don't see experimental evidence. So what we did later or earlier this year was actually we did synchrotron UPS on silicon quantum wells embedded in silicon nitride and silicon oxide. Both have a thickness of about 20 angstrom. And we also had a hydrogen terminated silicon wafer as a reference. So basically it was etched by buffered HF and kept under nitrogen shower while being sampled, mounted on the sample stage, and then put in load lock, etc. And what we see for the silicon quantum well in silicon dioxide, we are 0.87 electron volts below the valence band edge of bulk silicon. So this is not surprising. We'd think it's quantum confinement, etc. It's fairly large, but it looks plausible. If we look at the quantum well embedded in silicon nitride, we actually get a highest occupied density of states edge of 0.02 electron volt above the valence band edge of bulk silicon. It actually gives you a slight type 2 band offset. And this difference comes about because of the embedding in different dielectrics. And because we know from photoluminescence that the gap of silicon nanocrystals in silicon nitride is bigger as compared to the ones in silicon dioxide, we can presume that the offset between the lowest unoccupied states is bigger than 0.9 eV. And thereby you can actually generate P and N type preference in silicon, and thereby again you can build undoped devices. Okay, that was just a digression onto the interface charge transfer and where these number series play a role. The next point I want to talk about is the further partitioning of the number of interface bonds depending on the faceting. And there was actually some really nice work being done by Ivanescu and Stesmans back in 2008 and earlier. The key point here is that you have PBO defects which are located at 111 facets, and you got the PB1 defects, dangling bond defects, silicon, at 001 facets. Most of you will probably be more familiar with the PB1 defect because we use 001 silicon in solar cells for passivation reasons. And these have different signatures in electron particle magnetic resonance, so we can actually discriminate these very well. And back in 2008, UNSW and Stesmans just kind of guessed it probably looks like the crystals look like that, and but they didn't really know. They called it idealized average morphology. Now, what we can do with these partitions of interface bonds and the quadrodecahedra types we have, we can calculate the ratio of both partitions, and as a function of size, again via the run index. And what you see is very nice. You see the asymptotic limits here for infinite, or basically crystal size approaching infinity. And you see there is no overlap. And that means you can either, what's the more likely case, know the size of your crystals, roughly, and you get the shape partitions, or you turn things around if you know the shape already, because you have a certain etching process or whatever, you can derive the size or size distribution. So that actually gives a very nice handle on further interpreting EPR data. The last point I want to talk about is the ratio of nanocrystal, so internal nanocrystal bonds per nanocrystal atom. And this has an asymptotic value of 2, because every silicon atom in the crystal has 4 next neighbors. Or gallium arsenide has 4 next neighbors, but each of these 4 bonds is shared with another atom, so it's basically 4 divided by 2. Alternatively, you could say, okay, we choose the coordination number, which is 4. But I rather like to stick to the bond because that directly corresponds to the number of bonds within the nanocrystal. So you don't have any double counting terms. Now, there's been a lot of work on so-called self-purification. I'm, in the meantime, not very happy about this word because it doesn't mean there are no impurities within the crystal. It's just they are not on lattice sites, so they can't be activated as such. And Stegner and Pereira did some very nice work back in 2009 where they generated silicon nanocrystals with silane and phosphine in the plasma phase, and then investigated basically the number of built-in phosphorus, so on the lattice side, as a function of nanocrystal size. First, they etched off the air oxide, and that already removed 95% of phosphorus. And the phosphorus atoms with an unpaired electron on the lattice side are shown by this red line here. And we see between 20 and 10 nanometers that there's a decrease in 2 orders of magnitude. So it doesn't make sense actually to go below 20 nanometers if you want to dope nanocrystals. We all know that actually from polycrystalline silicon cells, the huge majority of the dopants actually ends up at the grain boundaries. That's the same effect. They kind of get pushed out. And if we now look at the ratio of nanocrystal bonds per nanocrystal atom, between 20 and 10 nanometers, we come from around 1.96 to 1.92. And this is actually for the silicon nanocrystal silicon dioxide system, because again, that also depends on the matrix and the stress imposed on the nanocrystal. We see that this ratio gives us the limit below which doping of silicon nanocrystals in the conventional way does not work. And again, because that depends on the shape of the nanocrystal. So say you have an elongated nanocrystal where this ratio actually is lower, you may shift that to 30 or 40 nanometers, depending on your structure, which again is important for FinFETs, because there you have to use a flash anneal to build these dopants into lattice sites as well. Another point for the ratio of nanocrystal bonds per nanocrystal atom is Raman spectroscopy. And I'd like to talk about so-called breathing modes first. They are very common or often observed in organic molecules like fullerenes, like C60 molecule vibrating. And it's a longitudinal acoustical mode. if you look here, you can see actually all the atoms moving in unison out and back in. And we can actually use a reciprocal space picture to describe the frequency dependence. So if you have a very small crystal, you would be at a very large K vector, so near the Brillouin zone edge. And as the nanocrystal size increases, you slide down the longitudinal acoustic subband, eventually arriving at 0 for infinite crystal size. And as you can see here, that approaches eventually. I mean, these are very small crystals. They're actually big for DFT, but in terms of real samples, they're rather small. So you would slide down here towards the asymptotic limit, which is 0, but because there is a hyperbolic relationship between real space and reciprocal space, it means you go down very fast in the beginning, then you slow down a lot as you increase nanocrystal size. So you're not immediately going to 0. Now this brief mode has a low electromagnetic dipole moment simply because it's an acoustic mode, and all, I mean, if say you got beyond 3/5 and you got, let's pick say indium phosphide, which is relatively polar, both positively and negatively charged atoms actually move in the same direction. So the difference between two atoms to form a dipole is very small, and that means we could actually use a force constant model to describe, basically with the help of the number of nanocrystal atoms and nanocrystal bonds, to describe what's happening. And the interface termination obviously also has an influence on the longitudinal acoustic wave number. If they have a higher mass, the wave number goes down, as you can see here, but also the intensity goes down, simply because of damping. And the shift of the breathe mode by the embedding is rather small. We see here we have a hydrogen terminated silicon 10 nanocrystal, sorry, a amino terminated one, and then we put that in 2 monolayers of silicon nitride, and we actually lose quite a bit of intensity, but little in terms of wave numbers. So the damping is actually strong because the nitride is also really, really hard. So it kind of stops the nanocrystal from vibrating. If we look at silicon dioxide, the story is similar. What's a bit puzzling is that chlorine appears to be a runaway. So the wave number is not as low as it's supposed to be, but the intensity is higher. However, if you think about the atoms in mass terms, right, fluorine has a mass of around 19, hydrogen obviously 1, silicon is 28.1, and chlorine is 35.4, and bromine is around 80. So chlorine by far is the nearest in terms of mass to silicon, and that effectively provides us with a vibration of a hydrogen-terminated silicon 35 cluster, kind of. And this is why we see these runaways. Now, with all these wave numbers, or calculations I did, and the force constant model, I looked into coming up with a fit of these data. And what we do there is as we know, it mostly depends on the ratio of nanocrystal bonds per nanocrystal atom. We use that form of the fit and put in the wave number of the lowest, or basically the smallest crystal, to include the interface termination and strain. And you see a lot of limits here against infinity. So if we replace these with numbers and the starting value, we end up with that relatively simple fit. And you can see for hydrogen termination and for, mostly for hydrogen termination, the fit's really good. For fluorine and hydroxide termination, it's also pretty good. It's not so good yet for amino termination and chlorine termination. But, well, for chlorine, actually, that could be due to the resonance. So there's obviously more work to be done on the model. Another very interesting Raman mode is the silicon bark mode. That is usually referred to get the nanocrystal size. And this is kind of working for freestanding nanocrystals. But if you look for nanocrystals embedded in silicon dioxide, it does not have a real preference. And this is actually a very nice work from a Chinese group in the Journal of Physical Chemistry Letters back in 2012. And they used different models here. See all these dotted lines and a least square fit. And obviously the least square fit gives you, in terms of statistics, gives you a good description, but it kills all the causality. So you have a purely empirical description, and you don't know really where it comes from. You can try to search for different processing conditions you used. So it would be good to have an analytical fit for the nanocrystal species to allow for real data interpretation. So we can go back to the nanocrystals and have a look. And I first will have a quick look on this fundamental optical mode we see in silicon. Again, we have this Burian zone picture, but because we now have a longitudinal optical mode, we start with the smallest crystal, so large K vector, and we approach the back value, which is 521 per centimeter from below, because we are now on optical subband, not an acoustical subband. And the mode is not clearly assignable because it's, as you can see here, it's both. It's longitudinal and it is transversal. So it's a mixed longitudinal transversal mode. But I think it's quite instructive if you do Raman measurements that you kind of know really how these derivations look like. You can see the same atoms here actually in the silicon 84. So 1.5 nanometer nanocrystal. Now for the fit, we have to use different boundary conditions. We start with again with the wave number of the lowest or the smallest crystal, and add the difference. So that's the limit in infinity or for infinitely large crystals. So that's 521 per centimeter. And because we subtract that, and this term, the beginning is 1 because A of I, as you shall see, is the same as A of 1. Sorry, it's 0, so we start actually with that value. But if we go to very large values of I, we see that this term actually turns to 0. So we add this difference as well, and we end up at the asymptotic value for bulk silicon. This term A of I is very interesting because we have two influences here. The first one is the number of interface bonds, the ratio to the number of nanocrystal bonds. That obviously goes down and approaches infinity. Approaches 0 for infinitely large crystals. But then we also have the number of bonds per nanocrystal atom. And since we have an optical mode, we actually reverse that and use the asymptotic value for an infinite crystal. So both the interface termination relative to the number of bonds in the crystal, as well as the number of bonds per nanocrystal, go into this coefficient. And we see a fit here for hydrogen-terminated crystals. So that's the silicon 10 nanocrystals, silicon 35, silicon 84. And these are experimental values which are alkyl capped. And this is not exactly hydrogen because you couldn't redo that in experiment unless you keep it under UHV all the time. But the interface conditions are kind of similar because the bond is fairly covalent. The electron affinity is similar between carbon and hydrogen, and the difference in electronegativity is also about the same. It's a bit bigger, but not much. You can see quite nicely that the fit describes the Raman wave number as a function of nanocrystal size quite well. So this could be quite useful to look at nanocrystals. And that will be important for colloidals, because if you have embedded nanocrystals, as we have seen in experiment, the points are rather scattered, so it's not a good idea to use that for size estimation. Okay, I'd like to wrap up now. I've shown 7 different high symmetry Zinc-Blende or diamond lattice nanocrystals, and gave an analytical description for the number of atoms forming that nanocrystal, the bonds between these nanocrystal atoms, as well as the interface bond to the exterior. And with these, we can actually come up with several ratios to describe the nature of the nanocrystal. So for instance, for the stress balance between the Zinc-Blende nanocrystal and the embedding matrix, like crystallization limit and the onset of polymorphism, you can use the number of interface bonds per nanocrystal bond. Then the ratio of interface bond per nanocrystal is very important for the electronic structure if you have very strong anionic ligands or embedding. And we can go further with the interface bonds to clarify the morphology or size, depending on what you know first, of silicon nanocrystals and presumably other zinc-blende nanocrystals by electron product magnetic resonance. And the ratio of nanocrystal bonds per nanocrystal atom is also describing the stress response. Very nice. So in terms of impurities, stacking faults, dangling bonds. And currently I'm working on analytic Raman fits, which will maintain causality, so you can actually really go back and check on the crystals. And again, if you need any more details, just look up that DOI, which has all the formulas, which I didn't show here because I don't want to torture you with the maths, really. Okay, so we got a few minutes left, so if there are questions, shoot.
So Dirk, we had some discussion, I think, around the time when you were finalizing the manuscript about the relationship or contrast between what you've done here and some of these other methods which have been developed for predicting morphology and so forth of nanoparticles. Could you maybe give a quick summary of how that kind of panned out when you looked at the different methods?
Well, Amanda Barnard from CSIRO in Melbourne has now been working for 20 years, I think, or at least 15 years on computational descriptions of optimum nanocrystal shapes, of numerous materials, not just Zinc-Blende or diamond lattice, but also hexagonal lattices or trigonal lattices like metal clusters, etc. And these approaches also take into account surface tension and other more refined phenomena, but the calculations are numerical and extremely expensive. So these methods we got here are analytical. You can in principle use an Excel sheet if you want, So that's for an experimentalist, that's really great because it's fast. It's also good for DFT because you can kind of design approximants, as I said earlier, and that pushes your system size to bigger sizes. Amanda also found out in a recent paper that the phenomena like surface tension do not play a major role if you go beyond 10 nanometer crystal size. I didn't look into comparing that to my results yet, because if I go beyond 10 nanometer crystal size, there's not too much happening either. But as we've seen with the self-purification, it's still enough to make a difference in experiments. So I think I probably should contact her and we should collaborate on that, because if you come up with a hybrid, that would be very, very nice. So basically using my results as a shortcut to get very near the solution and then just kind of put numerics on top. That would be very helpful.
Any other questions?
Thanks. It's very nice to see that with a few numbers you can say so much. One of the things that you're aware of is when you actually try to grow this stuff, you get a distribution. And we've seen that it's the distribution itself that determines the shape of your PL or any spectra that you take out. So can you see an easy way to overlap this too, so where you can use this more analytical part and put it into this distribution of sizes so that you can actually work out what you have?
There's actually two answers. I mean, it depends on how much excess silicon you put in the samples and on your processing, because I know groups which have fairly regular crystals, but then depending on what you want to do with the crystals, you may put in so much silicon that you get a kind of interconnected network because that's more conductive. If you do that, then you obviously get crystals of elongated shape, and that goes into kind of a nanowire description. I'm actually looking, well, I don't have the time at the moment, but next year that looks a lot different. I can then work on these nanowire descriptions because that's also very interesting for the ULSI industry. And what we can do there is actually quite nice, because we treat the crystalline structure only 2 dimensions, so we get a degree of freedom, so we can actually play with faceting or ratios, which you really can't with these crystals. because you would get a two-dimensional number series, you know, but then it gets really iffy if you want to find the right point, etc. So yeah, in principle you can do that. Yeah. It would make things a lot easier though if you had regular crystals, obviously.
Well, no, but the case for crystals that are in solution, they still have a fairly large distribution in size, and we've seen it in PL, for example. That if you go and look at the PL spectrum, in the end it's overpowered by one of the sizes, but tails that you see are determined by what you have there. The crystals are very well defined because they're actually isolated. However, interpreting the spectra is difficult because you have to come up with a distribution. So this is why I was wondering, I mean, is it possible to embed this easily into a distribution and then be able to extract curves like
the crystals have, yeah, in principle you can do that if you have you basically weight the different members of the number series, right? What you need is the size information. So what's your main value? What's your standard deviation? Do you have a third moment in the distribution, which you usually have?
But that's actually the difficulty, right? Because you don't know, you have a spectra, and then you're trying to extract information from the spectra.
But you need the size information. You obviously need the size information, or you know what shape your crystals have. So I mean, you can't have both, obviously, because you otherwise you would have to meet an assumption. However, on nice crystals, I would suggest you talk to Richard Tilley, because they make very, very nice they have 2.2 nanometer, 2.6 nanometer crystal classes they use for medical applications and other stuff. So you also can filter nanocrystals quite successfully with zeolites. And I don't know how far that actually goes, that you can buy narrow distribution nanocrystals, but I think in colloidals, or in basically in nanocrystals prepared in liquid, like say oxidized and back edge nanocrystals, this is not, I wouldn't consider that as a major problem. Yeah.
More questions? If not, let's thank Dirk again for sending. Thank you.
Thanks, sir.